Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now before moving on to the second order integrated rate law, I want to take a little segue and talk about the half-life for first order reactions. So reactions are sometimes described by the time taken for a reactant concentration to decrease to half its original concentration, and this is called half-life, and it's also represented as T 1/2. And so now I'm going to show you how to calculate the half-life for a first order reaction. And so we just found that the integrated first order rate law is the natural log of A equals negative KT plus ln A0, which is the concentration of A at time 0. So now at T equals the half-life, the concentration of A is going to be half the concentration that we started with, right? Because that's the definition of half-life. It's the amount of time taken for the reactant concentration to decrease to half of its original concentration. So now all we have to do is substitute in this value for A. So we do ln 1/2 A0 is negative KT, but now the T is the half-life, so let's do T 1/2 plus ln A0. And so from here we do ln 1/2 A0 minus ln A0 by moving this over to the other side, and this equals negative KT 1/2. And so from here we can group these two together and do ln 1/2 A0 over A0 equals negative KT 1/2. And so we can cancel these guys out and get a value of negative 0.693 when we do the natural log of 1/2, which is equal to negative KT 1/2. And so from here, when we solve for the half-life, it's going to equal 0.693 over K, which is also the slope or the rate constant. And so this is a really important equation to know for first order reactions. And so you can calculate the half-life or the rate constant given one or the other. So now let's move on to doing the second order reaction integrated rate law. And so when you go from a reactant A to product B, the rate is written as negative 1 over A dA over dt, which is Ka, but now to the power of 2 because it's a second order reaction. And so this is the second order differential rate law. But from here, we want to separate the variables for A squared equals K dt, and then we want to integrate it to get 1 over A equals KT plus B, and then at a time of 0, 1 over A naught is going to equal the y-intercept like we did for the first order reaction, and therefore the second order integrated rate law is going to be 1 over A is KT plus 1 over A naught. And this is the second order integrated rate law. Here we go. Okay, so now as you can see, it's written in the form of y equals mx plus b again. So we can draw the plot like we did before. This is time. The y-axis is going to be 1 over the concentration of A. There's going to be some point, which is going to be the y-intercept, 1 over A naught. But as you can see, the slope this time is positive. And so let's put 1 over A naught right here and give it a positive slope. And so now the slope is K. So if the straight line fits to the data, then the second order reaction will have the slope of K. And so from here, we can also calculate the half-life for a second order reaction, just like we did for the first order rate reaction. And do 1 over A is KT plus 1 over A0. And then at time is T1/2. We have the concentration of A being 1/2 of A0 and 1 over A being 2 times 1 over A0. So basically, as soon as you figure out the relationships based on the definition of half-life, you're going to be able to derive any of these equations. And so from here, we can rewrite this equation as 2A0, which equals K T1/2 plus 1 over A0. And from here, 1 over A0 is KT1/2. And therefore, the half-life for second order reactions is 1 over K A0. So it's a different equation from the first order half-life equation that we figured out before. And this can be used for the half-life of all second order reactions dependent on the initial concentration of A. So we went over first order and second order reactions, but there's actually also one final one called zero order reactions. And this is a rate of reaction that is independent of the concentration of the reactants. And this often occurs when a catalyst or an enzyme is required for the reaction to happen. And so when we go from reactant to product, the rate is going to be negative 1 over A dA over dt, which is K A to the power of 0, which is just K. So what this means is that the surface of a catalyst or an enzyme is saturated, and increasing the concentration of the reactant will not increase the rate of the reaction. And so the rate is limited by K, the rate constant. And so from here, we can separate the variables again and write this out as dA is equal to negative K dt. So the concentration of A is negative KT plus B. And at t equals 0, this can be written as A equals negative KT plus A0, which is the initial concentration. And so this is the integrated zero order reaction, and we can plot it since it's in the form of y equals mx plus b, and it looks very similar to the first order reaction, just with a different y-axis. So we have time here, and here we would have A, the concentration of A, and so there's a point where the y-intercept occurs, which is A at time 0, and then it's going to be a negative slope, where the slope equals negative K. And so we can also calculate the half-life for a zero order reaction, and we can do A equals negative KT plus A, and then at T is the half-life. The concentration of A is going to be 1/2 of the initial concentration of A, and so we would have 1/2 A0 equals negative KT1/2 plus A0, and from here we would get 1/2 A0 equals KT1/2. Therefore, the half-life for zero order reactions is the concentration of A at a time of 0 over 2K. And so the half-life for a zero order reaction depends upon the initial concentration of the reactant.